Hi, it's Bruce again, and welcome to my Colorado Rocky Mountain lab. And what I've been working on this week is this ESI Decaviter DV411. It is in really nice shape, beautiful shape, nice paint, and everything worked on it except I found that somebody had burnt out, not completely, but had damaged the pot. Those pots are extremely linear, hard to come by. I wasn't real happy when I discovered that, but you take your chances when you buy these things. So what I decided to do, until I can come across a replacement pot at a reasonable price somewhere along the way, I disconnected the pot and I outriggered a 10-turn pot in this box here. There is also another pot in the back. So there are two 10-turn pots in here. One is 100 ohms, which essentially replaces the internal. The other one is 10,000 ohm that I pulled out of the box. Probably if I'd have had 1,000 ohm I would have used it, but I used a 10,000 ohm. Basically that 10,000 ohm is a variable resistor that parallels the resistance of this 100 ohm pot. Now that 100 ohm pot is rated at 5% and actually measured out at 104 ohms. And by placing this 10,000 ohm pot across it, I was able to vary the resistance till I got it down to around 80 ohms, which is where I want it to be in this Kelvin-Varley divider circuit here. So in calibrating this device, I set the first 3 decades to 0, and then I put my fourth decade, this 10-turn pot, I set it 9.90. And with 10 volts coming in from that fluke into the input of the divider, I expected to see 9.9 millivolts coming out. I adjusted this rear pot until I saw 9.9 millivolts on my voltmeter. Then I assumed I was calibrated. Now at that point, I can test it by, let's say we go down to 8. Okay, so I've dialed in 8, and we see that we've got 0.008 on the meter. And if I was to go down to 7, we should see 7 on the meter. So we do. So that's great. So let's go ahead and do a calibration on this device and see where we wind up. I am reading, by the way, on the 10 gigohm input impedance on the meter. I do not want to load this Kelvin-Varley. I want to be as light a load as I can be, so that would put me up in the maximum. I have myself set in the manual ranging, so I've got 4 decimal places showing, so I can read the first decimal whole number and then 4 decimal places, and it'll keep that throughout the entire test. That's because we have a 4-decade, essentially, meter. This would be ones, this is tenth, hundredths, and then we got thousandths and 10,000ths on this outrigger. Alright, so we're going to go ahead and give it the test. Let's give me a moment and we'll set this thing up. Okay, well, what we're going to do now that we're set up is we're going to run this thing through a calibration test. So we're feeding the 10 volts in. We are set for 99999, and we are reading all nines. So recording that, we got it. Let's go ahead and turn our most significant digit down to 8. We see we've got 8 and all nines. 7. 7 and all nines. 6. 6 and all nines. 5. 5 and all nines. 4. 5 and all zeros. It's flashing between all nines and zeros. I'm going to call it zeros. 3. 3 and all nines to, well, we'll call it 4 and all zeros. 2. We got 3 and all zeros. 1. We got 1 and all nines. Let's go to 0. We got 1 and all zeros. Okay, we go to 0.8 and all nines. We got 0.9 and all zeros. 0.7 and all nines. We got 0.8 and all zeros. 0.6 and all nines. We got 0.7 and all zeros. 0.5 and all nines. We got 0.6 and all zeros. 0.4 and all nines. We got 0.5 and all zeros. 0.3 and all nines, and we got 0.3 and all nines. All right, good. 2 and all nines, got 2 and all nines. 1 and all nines, 0 and all nines. Now taking the third significant digit from 9 to an 8, we got 0.0899. To a 7, 0.0799, to a 6, 0.0699, 0.0599, 0.0499, 0.0399, 0.0299, 0.0199, 0.0099. At this point, it's my outrigger that's totally in control of the digits that are left. All right, I'm going to go from 99 to 89 on the dial. Should be it. There we go. And we get 0.0089. That's good. I'm going to go to 79. Should be there. Yep. 69. What about, oh, I'd say there. Yep. 59. Should be there. 49. Should be there. 39. Should be there. 29. Should be there. 19. Should be there. 0.9. Actually, yeah. 0.9 should be there. 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, 0.1, 0. And there we go. So now, okay, we've got all of those results are recorded. We're going to put this into the computer, into an Excel spreadsheet, and we'll look at the results. So bear with me, it takes a moment to do this. Okay, I input all of my numbers into the spreadsheet, and what I'm seeing is that we have a maximum error uh, that we can observe within the first 2 decades of the maximum is 0.02%. 0.02%. So that's 2/100 of 1%. That's our max error. We began with an error that was around 0. We started to rise in the thousandths of a percent until we got to the 0.02. And then around 0.3999, we started at 0 and we maintained 0% error all the way down until we hit the end. So this thing is working remarkably well. The specification says 0.05% maximum error. I got 0.02. I'm certainly not going to be upset. And like I said, this is using my outrigger device, so it was successful. I'm happy with the way that's turned out. I'll be able to use this unit until such time that I can get a replacement pot, which I'm not going to be bothered whether that's soon or later. But so there we go. And if we, just for kicks, turned ourselves first decade back up to 9, we got 8 and all 9s, which would make sense. We'll go ahead and bring in the other 2 decades. All right, there we got 9990, 9990. So we're in good shape. Beautiful unit. Thanks for listening.